Hello, my name is Richard Hayman. I've been a sailor all my life and hold a U.S. Coast Guard Merchant Marine Officer's license. And in my many years at sea, I've studied propulsion technology in shipbuilding and in different alternate forms of propulsion for ships and small craft. And I became interested in the water turbine designs of Gorlov, the Russian scientist who is now at Northeastern University. But his water turbine helix foil is a capture system for water flow to then generate electricity. My other study was with Schauberger, the Austrian hydrologist and engineer who studied the pressure differences in fluid vortexes to induce flow and to create a kind of a more naturalistic study of stream beds, irrigation, and pumps. So what I've conceived of is a crossover of this technology into what I call the vortex propulsor, or the Vor-Prop, which is a device that we have a prototype here to induce a water flow using hydrofoils in a helix construction to thereby create a vortex flow through the propulsor and then to provide thrust for a vessel. Now, what the difference between capturing the energy of a flowing water and then driving a propulsion means that the flow is actually turned from perpendicular in a turbine to horizontal in the Vor-Prop. And now this particular model that we built for visualization and for some testing has bronze helix foil, like an airplane wing, but a hydrofoil version of them. Then they were put into this armature so that we could visualize it and then see it and build onto it if we need. Now, this is now being done in computer prototyping at this point, but this was our first constructed prototype that when it gets moving, you can see that there would be a cutting like a standard screw propeller that would then draw by the pressure difference of the hydrofoil. The low pressure would be in the center of the Vor-Prop with or without this shaft. This is just for demonstration purposes. And the armature would not allow the flow to properly be tested. But the low pressure would be in the center, and then a large flow of water would be induced. And the larger the flow of the water, the more you get a propulsive thrust. The screw propeller has evolved over many decades to many applications and variations depending on its speed, its load, the design of hulls, etc. But the common characteristic are a number of blades with a cutting edge, a push and pull of the water, turbulence created by the blades, creating propeller wash, chaotic vorticities, and again, deterioration of the metal through the high pressure and the draw of gas out of the water. In our computer analysis of the Vor-Prop, we simulated a standard screw propeller of the same size and same rotational vectors for contrast with the Vor-Prop effect. The hydraulic flow analysis shows a low pressure ahead of the propeller and a low pressure cone after it, but the red tips are the edges of the leading edge of the standard screw propeller. Our data set captures the screw propeller as it cuts its own path in a cylinder with alternating chops of the propeller blades. The Vor-Prop, in contrast, as simulated here, is in its own cylinder, and the helix blades will create a pressure differential as the Vor-Prop turns by either shaft mounting or other means of power applied to the Vor-Prop. You can see in the cylinder that the low pressure is gathering in the center of the Vor-Prop, and the hydrofoils are inducing a vortex that is blue. The higher pressure are red. These are the tips of the Vor-Prop as they begin to create the hydrofoil effect. Here, the red is the high pressure, the blue is the induced low pressure, which gathers along the Vor-Prop. As the Vor-Prop develops its flow, the high pressure is to the exterior of the Vor-Prop The blades are inducing a low pressure, and then at the aft of the Vor-Prop, a low pressure vortex begins to develop. In this view of the Vor-Prop, the helix blades are in red with the high pressure on the outside of the blade, and then the blue low pressure being developed in the center of the Vor-Prop, creating pressure differentials to provide propulsion. The more water that is drawn in by the Vor-Prop and sent aft in a vortex, the greater the thrust is developed by the Vor-Prop. The key benefit that the Vor-Prop may provide is efficiency, fuel efficiency, low vibration, low noise. We imagine this could become an element in major shipbuilding with a cylindrical Vor-Prop built into the hull of ships. The longer and larger, the more efficient the Vor-Prop would provide propulsion. It may not replace the screw propeller or rudders for maneuverability, but it may provide a cruising speed that will be far more efficient than the screw propeller. The goal of our research is to establish the hydraulic principle as proposed with the vortex propulsor. And as we continue our hydroflow analysis, we will redefine various parameters and then lead to a 3D printed prototype for water tank testing. And this will lead to a number of variations or refinements which will lead to applications in the marine industry and other industries as the Vor-Prop indicates. Thank you for your interest in this project, and if you have any suggestions, please feel free to contact us. I'm Richard Hayman, and I thank you for watching. Happy sailing.